Good morning, everyone. Okay, we're gonna go ahead and just get started. Okay. Okay, so first up, a couple announcements. Quiz 8 opens today at 11 a.m. and it closes Sunday at noon. Make sure that you get started over Module 18 over the weekend. Module 17 reading assignment is actually finally due Monday at 10 a.m. And then the homework for both of these will be open up until the start of the exam on November 11th. On Monday, we are going to start on Module 18 in class. There's no attendance code this morning. I'll try to open one once I get you guys working on a problem. Okay, so we're going to start off kind of simple with a combination problem here. So this is going to bring some stuff back from a couple chapters ago. So what I want you to do is copy this down, and then I'm going to move you guys into breakout rooms. And while you're in a breakout room, I'll open Top Hat and get an attendance code for you.
Dr. V, did you make me a co-host?
Mm-hmm. Okay, and then what happens?
Esterification?
Yes, yeah, this is Fisher esterification. So these conditions should remind us of acetal forming conditions, right? They're the exact same thing, but we know that we're going to make an ester instead of an acetal because we're reacting with a carboxylic acid. So we end up making an ethyl ester. And you're also always welcome to shorthand that if you would like by writing OET. Okay, are there any questions on this problem?
No.
Great. Okay, so these two are only going to make sense if you made it through the later modules. So let's go ahead and work through these together just because I have a feeling that not everybody made it through all of the modules of chapter 17 yet. So what happens in the first step here?
It is oxidized.
Right, and is Jones a strong oxidant or a mild oxidant?
Strong.
It's mild.
It's strong, yeah. So our secondary alcohol is going to get turned into what?
Ketone.
Right. And then our primary alcohol gets turned into what?
Carboxylic acid.
Right. Okay, did anybody make it to the later modules in chapter 17?
Yes.
I did not.
Okay, I heard yes from a couple people. Does anybody recognize this structure?
It'll
Is that
hydrolyze.
aniline?
No.
And then like a lactone with
No.
oh.
Does beta
Is it a
acid ring a bell for anybody? Okay.
Yeah.
So, okay, we've now made a beta keto acid, which just means that on the beta carbon of this carboxylic acid, there is a ketone. So what happens to beta keto acids when they are heated up? I mean, heated up in general, but especially if we're heating it up in acid, what's going to happen?
It's going to
gonna protonate.
the beta carbonyl attached to the it's gonna rotate and you're gonna get a 6-membered ring.
And then what happens? What's the end product here?
The ketone.
Yeah, so this is setting us up for a decarboxylation. So when you have this beta keto acid structure, where you have the ketone in the beta position, what ends up happening is you're going to essentially lose an equivalent of carbon dioxide. So we're going to be left with a ketone and carbon dioxide as a byproduct that would leave the system as a gas. So that's in the, I believe, the very last video of chapter 17. Okay, the next one, what happens in the next one? Justin, the hydrogen does not go with it. The hydrogen that is here actually ends up here. So we can go over the mechanism on a blank slide at the end of this chapter, or at the end of this problem session, just so we can all see that together. What's going to happen in the next reaction?
Is it gonna break that ring open?
Basic exit
No, we're not going to break the ring open.
Won't it break down the ester?
Right, so this is a beta keto ester. So a couple things are going to happen. We have H3O plus, and we know what happens to an ester when it's reacted with H3O plus, right? It's going to hydrolyze. Whoops, sorry, I started drawing benzene. So we end up with the carboxylic acid. And then we're in the same place that we were a second ago. We have a beta keto acid. The heat is going to cause it to decarboxylate. So I gave you two different decarboxylation problems together because for some reason when I give something that looks like this, it doesn't click for people, and I think it's because the mechanism that you see looks, or it starts with something that looks a lot like this, and so you guys tend to not see this as a beta keto acid and a decarboxylation. So that's what your two possible decarboxylation setups will look like. We also could have decarboxylation with a malonic acid. That doesn't look very different from this, right? That would just be if you had a carboxylic acid on the other side. So definitely go over your notes if you haven't yet done this part of the chapter. Okay, I'm going to put you guys into your breakout rooms. So go to your breakout rooms once you've copied down this problem. Okay, how did you guys do on this one?
I
Not
think I
so-
got it.
Okay.
Okay. Okay, so let's talk about this. So we have an amide and we have an anhydride. Which one of these species is more reactive?
The anhydride? Anhydride.
Right, the anhydride is more reactive, and the amide is the only one that could possibly be nucleophilic. So that's going to be the
Right.
one that is going to initiate the reaction here. So what's going to happen?
Nucleophilic attack on the anhydride.
Right, so the amide is going to attack the carbonyl. So I want to go over it real fast. This is kind of the point where a lot of people start getting confused when you have just a lot going on in a structure. Remember to kind of simplify it in your brain. If you're looking at the structure and you're like, oh man, I'm very lost, make it simple. So we're making a bond from the nitrogen to the carbonyl carbon. So that means that this right here is the carbonyl carbon, and it's going to have a methyl group. It's going to have a negatively charged oxygen, and then it's going to have the rest of the anhydride on it. And then we're going to have a positive charge on the nitrogen. So that's all you have to worry about there. What's going to happen next?
Will we reform that oxygen?
Right, we're going to reform the pi bond, and this will kick out the other part of the anhydride. So we're going to kick out a carboxylate. So remember, we still have this methyl group here. So I just cleaned up the structure and put the methyl group here so that it wouldn't be gross looking. And then we have the equivalent of acetate that we just made. And we're just going to finish it off by deprotonating, because that nitrogen is pretty acidic at this point, especially since it's between two carbonyls there. And so that leaves us here. Okay, how many of us got this as our answer?
I got it. I just forgot to put the alcohol.
Okay. Okay, I'm seeing also in the chat some commentary about like the breakout rooms being quiet. You don't have to know the answer. I want you guys to sit there and talk with each other. Like if you're all lost, say, I'm lost. I have no idea what's going on. And then try to work through it together. That's the point of the breakout rooms. I haven't been able to go to them and help you guys as much because I'm mostly bouncing around and putting people into breakout rooms when they get kicked out of the meeting and brought back in. Okay, so here is our next problem. I'm going to go ahead and put you guys in the breakout rooms again, and I want you to work together. So even if you are 5,000% lost and you have no idea, say the first thing that comes to your mind and work through it together. That is the point of the breakout rooms. And hopefully I'll be able to come visit you guys. Okay, so what's going to happen in the first step here?
The NH3 is going to kick out the chlorine and replace it with NH2.
Right, so we're going to turn our acid chloride into an amide.
Yes.
Right.
Okay, and then what happens in step 2?
Formation of cyanide.
Not cyanide,
Are you gonna create an ester?
no. I think maybe
Nitrile
Warren
formation.
has the right structure, but just we need the correct functional group name.
Carboxylic acid?
Nitrile.
Yes, we're making a nitrile.
Oh, oh snap. Okay.
Okay, so the key thing here to be careful about is to make sure that you have the right number of carbons. So make sure that you keep that carbon number 4. And if you want to write in the letter C to help you out, you can. So we're making a nitrile. Okay, what happens when you attack a nitrile with a Grignard?
Formation of a ketone.
Right, so steps 3 and 4 together make a ketone. And again, make sure that you're careful with the number of carbons. Your ketone is going to be on your nitrile carbon. And then you're going to add 1, 2, 3 carbons from the Grignard. 1, 2, 3.
Wait a minute. You're telling me all of that just creates a ketone?
Yeah.
So we're not creating like anything extravagant? This is it?
Yeah.
Everything's with carboxylic acid. Carboxylic carbons and stuff, you know?
No, I'm
What
sorry.
is
I'm
what is
upset.
the P4O10 and heat? What is that? Yeah.
An oxidizer.
Yeah, it turns an amide into a nitrile. It's a single line in the notes essentially.
Okay.
There's that, and then there's another reagent.
I guess I have to
So
make
this and
Okay.
heat with an amide will do the same thing as P4.
Okay. Okay.
Yeah.
Yeah, I recognize the other one. Okay.
Yeah. Oh, I also
Thank
saw
you.
a question when I was reading back through the chat about the functional group we formed in the previous one. That functional group. Whoops. When you have essentially an anhydride with a nitrogen subbed in for the oxygen, this is called an imide. So I think somebody asked if it was a carbamate, and a carbamate is like a weird ester that also has an amide. So this is carbamate. So this is actually a functional group from the end of this chapter. This one I never gave a name to, but this is an imide. Yeah, there are so many more functional groups than you guys have learned. That was my graduate advisor's favorite thing to ask us during mechanism sessions, which were very painful, was to ask us about like obscure functional groups. And half the time, if you weren't sure, you could always guess like vinylogist something, and it was often the correct answer. But oh man, it was crazy. Okay, so next one. Do you guys want to go back into your breakout rooms, or do you want to work through this together?
Together.
Okay.
Yeah, let's do it together.
Yeah, we can work together.
Okay.
Breakout.
Maybe I'll start putting you guys into much larger breakout rooms. Or no, maybe I'll put you in even smaller ones. I don't know. One of those options is the correct thing. I just don't know which one. Okay, so in the first
I think
step,
you should do like 30 per.
30 people, and that's half the class.
Like maybe 10.
Okay. So we have a secondary alkyl bromide, and we're reacting with sodium cyanide. What's going to happen?
The nitrile again?
Yeah, so we are basically doing an SN2 reaction here. We're going to kick out the bromine. And this creates a nitrile. Okay. What happens when you put a nitrile in aqueous acid and heat it up?
Benzoic acid is made.
Not benzoic because it's not benzene, but yes, we're gonna make cyclohexane carboxylic acid is what it would be called. So remember, a nitrile is a carboxylic acid derivative, even though it doesn't really look like one. So if you put it in hydrolysis conditions and heat it up, because it's not particularly reactive, it's a lot like an amide in that way, you're going to end up with a carboxylic acid. Okay, and then what happens when we have a carboxylic acid and an excess of alcohol in acid?
Form an ester.
Ester.
Right. I love how quickly these reactions are coming to you guys. This is good. Okay, so that was just another Fisher esterification. So one of the things that I had talked to you guys about, I think it was on a Friday, I believe, was somebody had just asked, like, how can I make good flashcards? And I just wanted to revisit that idea real fast while we're, learning a bunch of new reactions. So remember that when you make a flashcard, it should be usable front ways and back ways. So no matter how that flashcard appears in your deck, it should be useful. So what I would do on one side is use something very general. And then on the back, so like this would suggest to you that you need to come up with the ester. On the back, if you just draw the you're going to get this flashcard and be like, an ester, great. And then you flip it over and you're like, oh no, that was reads. So what you could do is write like synthesis of ester from carboxylic acid, or you can draw out the carboxylic acid, leave the reagents blank, and put in the ester. So then if you look at it from the front ways, you're like, okay, I needed to come up with this. Cool, I have that. And if the card comes up to you with this as the front, then you know that you have to come up with the reagents, and they're here. So that makes this card usable in both ways. Whoops, did not mean to progress. Another good way to study this type of reaction would be to write down the name of the reaction. So write down Fisher esterification on one side. Sorry, that should have a C in there. And then on the other, write down something very general. Don't even draw out structures. Write carboxylic acid plus excess alcohol in acid. So this gives you a really, really, really broad flashcard on one side so that you learn to recognize those conditions. so that when you see something that doesn't look anything like this, that has like a really bizarre looking carboxylic acid, or maybe it has like a beta keto acid and it just looks a little too different, you say, okay, well, I see a carboxylic acid. The conditions have excess alcohol and more acid. So putting those flashcards into words can be really useful as well. So when you're making your flashcards, try to do something like that. Allison asked about for learning mechanisms. For learning mechanisms, I'm not sure what the annotation here is about. Yeah, I just doodled front and back on the top just for fun. You can use them either way, like this could be the front as well. So Allison asked, I'm going to turn off the annotations because it slows down my thing. Actually, it's not letting me. Okay. Yeah. So Allison asked, how about learning mechanisms? For learning mechanisms, honestly, the best thing to do is to just practice. Anytime the student has tried to memorize a mechanism, what you end up doing is you leave out small details and you end up losing a lot of points. Or you memorize like a very specific mechanism, and then if it's a little different, you get completely thrown. So I would draw out reactions. Like I already gave you guys the exact mechanism for Fischer esterification, and I gave you these exact reagents. So if you want to draw out this mechanism again, step by step, I think that's great, but do not have your notes open. Do not have your textbook open. Do not have any resources. The only way to learn a mechanism is to force yourself to do it, no matter how painful it is, and then go back and check yourself. So work your way through the mechanism. You know that the outcome of this is an ester. And then go back and check yourself. If you are copying down the mechanism, that's a memorization tactic, and that's not going to be helpful to you when you're expected to use the mechanism to figure out the product. Because here you know what the product is, and that can help guide you. But starting in a little bit in chapter 18, but definitely in chapter 19, the mechanism is what's going to help you figure out the product. So if you're having to second guess yourself and like use the textbook for mechanisms, it's going to be really, really hard. So yeah, unfortunately with mechanisms, it's practice and comparing to what you know to be the right answer. If you don't have something to compare it to, because maybe you're trying like some really bizarre mechanism, come to my office hours. I had office hours Monday and Wednesday this week. Nobody showed up. That's why I didn't feel bad about canceling on Tuesday. I went and voted instead because I knew that nobody was going to come, which is really sad. I want you guys to come to my office hours. So yeah, please come. Whoops, I didn't have any more blank slides. I promised that I would go over decarboxylation with you guys real fast. It's kind of a bizarre mechanism. I don't tend to ask about this mechanism too much. But sometimes I ask about why decarboxylation occurs, and that does come from the mechanism. So when you have a beta keto acid, which is what this is, and you heat it up, it doesn't actually take that much heat. It doesn't have to be like a super crazy temperature. You're going to end up with a ketone. Here's your alpha carbon, here's your beta carbon, and an equivalent of carboxylic acid, or carbon dioxide, sorry. So the first thing that happens in this mechanism is that you go through a 6-membered transition state. So remember that there's free rotation around this bond. We could draw the carboxylic acid the way that I drew it in the top structure, or we could also draw it by putting the carbonyl off to the side and the OH group out this way. So this is our 6-membered transition state. And what actually happens in this mechanism is it kind of has a cyclic mechanism. The pi electrons in the carbonyl bond here, oops, sorry, I'm trying to draw little dots, okay, are going to reach out and grab the hydrogen. And that's going to cause the bond between the hydrogen and the oxygen to break, which forms a double bond between the carbonyl carbon and that oxygen. And then that's going to cause this bond to break because this carbon can't have that many bonds. And that literally is the entire mechanism that happens there. You end up with what is called an enol, which we're really going to get into in the next chapter. And that goes through a process called tautomerization to form a ketone. We'll worry about that mechanism next chapter. It's not too crazy. So that's how you end up with your ketone. One of the really important things about this mechanism is that it is resonance stabilized. So if you think about the deprotonation of this carboxylic acid, which is not part of the mechanism. But imagine that you were to deprotonate the beta keto acid. You can form a double bond between the oxygen and the carbon, break this bond to form a double bond, and push electrons up onto the oxygen. That would give you what's called an enolate.
Thank you. I was wondering what the difference was.
Oh yeah, it's just a deprotonated enol essentially. So this is an enolate, and this has a resonance form that actually shows you how we get to the ketone essentially. So the resonance form shows the negative charge on the carbon. Now this is actually the reactive species that we're going to start worrying about in chapter 18 and 19. If you protonate this, you end up with the ketone. So the other really big reason that this reaction occurs, because it doesn't seem like it should occur, right? It's going through some really weird stuff. Oops, I'm going to try to pee and I wrote an N. The big reason here is entropy, because we go from one molecule, which is our beta keto ester, or beta keto acid, and we end up with 2 molecules. That is entropically favored, and entropy is a huge driving force in organic chemistry. So any reaction that's going to take one molecule and break it down into 2 is going to be a highly favorable process. And this is a favorite test question of mine. I love to ask about the driving force of reactions. And every time that I've asked this question, like less than a quarter of the class gets it. Because I know it's just, a single line in your notes, but it's really important because it's a huge driving force for a lot of the reactions that we're going to be seeing. And then we're also going to do a bunch of reactions where you actually have to kind of overcome entropy in order for the reaction to occur. So understanding that is really important.
So I had a question.
Sure, hold on real fast. We are out of time. It's 10:52, so if you need to leave, feel free to leave. Make sure that you checked in with TopPat. I did share the code earlier. Go ahead, Warren.
So before you are adding the CO2, well, taking away the CO2, I see why the pi bond bonds with the hydrogen. I see why the hydrogen bond breaks. That carbon to carbon bonds is breaking. Is that only due to the heat? Because otherwise, wouldn't the pi bond to the oxygen just break and form a negatively charged oxygen?
Well, so the reason that this breaks is because when you form that pi bond here, that step that you're talking about, It forms carbon dioxide, and this is really favorable. Forming carbon dioxide instead of just pushing the electrons here means that you are releasing a gas, which is a driving force, and also that's entropy right there. So this is the point where the molecule has a choice, like I could push the electrons onto the oxygen, or this bond could break. And it's entropy that causes that bond to break instead.
Because instead of having any charge, we now have a neutral atom and a neutral atom.
Right, we end up with two neutral molecules instead of one confused molecule.
Okay, that makes sense. My only, yeah, because I almost thought it was like a more substituted cation thing where it was going from a like a secondary position to a tertiary. I thought it was something like that. But no, it's just
no.
because the carbon dioxide is favorable.
Yeah, plus also if you did that and you push the electrons here, somehow that would create a negative charge out of a reaction that had been neutral. So I'm not even sure that that's possible, because you wouldn't have a positive charge anywhere in the molecule to neutralize that. Or I guess you would actually, you would have created a carbocation here. So yeah, that would end up with like the outcome of that particular process would be a carbocation here. So yeah, that's kind of a mess. Yeah, this system would much rather that you just created a double bond there and broke this.
All right, thank you. That answers my question.
Mm-hmm. Yeah, that was a good question. Okay, any other questions? All right, thanks guys. I'll see you on Monday. Have fun with your quiz.
Have a good weekend.
You too.